We transition now from trusses to frames and machines. As was mentioned earlier, frames are intended to remain stationary, while machines are intended to move. When we examine a machine in statics, we'll be looking at a temporary, stationary configuration. Our goal remains to understand how forces and/or moments are communicated between members of the assembly of rigid bodies. To understand this communication, it is often necessary to disassemble the frame or machine, sketching a free body diagram for each member and sometimes the whole assembly. The difference between our approach now and that with trusses is that frames and machines are not assemblies of two-force members. There may be one or more two-force members present, and it is a great advantage to be able to identify them, but members may be subject to any combination of forces and moments, and this generally complicates our analysis. The procedure for drawing free body diagrams is no different now than what was outlined in Chapter 5 for single rigid bodies. We just have more of them. Here I'll offer somewhat contradictory advice to what is listed at the bottom of the second slide, namely, tip draw free body diagrams for two force members first. Free body diagrams are a crucial precursor to writing equilibrium equations. However, two force members are, by their nature, already in equilibrium. Rather than drawing free body diagrams for two force members, I'd suggest just trying to identify them. Then focus on the elements of the assembly that are not two force members and draw free body diagrams for them. You may also want to begin by examining the supports for the whole system and determining whether or not it is worthwhile to draw a free body diagram of the whole assembly. Sometimes solving for reactions for the whole can help simplify the analysis of the individual members that follow. Here we have an assembly of 5 members, all pin connected. We are first asked if the structure could be a truss. The answer is no, and it is because of members ABC and CDE. Even though they are pin supported, the forces communicated at B and D are intermediate points between the ends, and this violates one of our assumptions of two force members. It is the case that BF, CF, and DF are two force members, and this will help simplify our analysis. Note also that we have a rocker support at A and a pin support at E, so the whole assembly is statically determinate. This will prove to be a useful place to start to find the reactions at those points. Finally, one further point bears mentioning before we begin drawing free body diagrams. Note that the force communicated by two force member CF acts at a joint shared by ABC and CDE. If we are isolating ABC and CDE, how do we apportion the load carried by CF between those members? Do we apply it all to ABC? Do we apply it all to CDE? Do we split it between them in some way? Does it matter? In the end, it won't matter how we apportion the load from CF, but we'll see that as we go through this example. Free body diagrams of the whole assembly, member ABC, member CDE, and joint F are based on these enveloping surfaces. For the whole assembly, we are capturing all of this. For member ABC, we have to cut through the two force member BF and the joint at C. We also have the 500-pound load at B. For CDE, we also have to cut through the joint at C, two force member DF, and for joint F, we're just going to isolate this. So this will be the basis of our free body diagrams. We're going to call these 1 for the whole assembly, 2 for ABC, 3 for CDE, and 4 for joint F. For the whole assembly, our free body diagram will look like this. We have a pin supported E, so we have two reaction components there. We have a rocker supported A, which functions the same as a roller. So we'll have the force A here. And then we have our 500-pound load here. And ideally, we should also put some dimensions on this to make it easier to draw our, or to write our free body diagram. So we have a 60-inch distance here, and we have a 200-inch distance here. Note also I could include some outline of the other members here if I wanted to do so. That's okay. It's not necessary because all of that is internal to our enveloping surface. For 2, for ABC, I'm going to choose to remove ABC from the remainder of the structure, and that will give me a free body diagram that looks like this. I'm going to be assuming that FBF is in compression, and we'll see whether or not I'm correct in that assessment. We'll also note here that this is a 3-4-5 triangle here. When I remove ABC from the joint at C, I have to represent some internal forces that develop between ABC and the remainder of the structure, so I'm going to represent those like this. And then when I draw my free body diagram for CDE, I'm going to have equal and opposite forces there. Now, one of the things that you may notice is that I haven't done anything with FCF yet, and I'm going to choose to put 100% of it over here on CDE. Now, you may wonder why I'm doing that, and I'll come back to this. It will not make any difference whether I put a portion of FCF on each member or whether I put it all on one member or all on the other, but we'll see why that is as we go through our solution. So then to complete the free body diagram for CDE, I'm also going to assume that FDF is in compression. And again, I'm going to end up with that 3-4-5 triangle slope here. And then finally I have EX and EY. And finally, I've got my free body diagram for joint F, and that's going to look like this. So I've drawn FCF as though it's in tension. That's what's assumed. That's what's implied on my free body diagram 3. So I'll have an equal and opposite force here for FCF. And then I've drawn FBF and FDF as though they're in compression. So I will try to reproduce that here. Now, if we've done all this correctly, we should be able to put 2, 3, and 4 back together, and all of those internal forces should cancel out, and it should give us the free body diagram for 1 for the whole assembly. Note that between the 4 free body diagrams, there are 8 unknowns: A, EX, EY, CX, CY, FBF, FCF, and FDF. The four free body diagrams are not independent of each other. We need to impose equilibrium on two of the three bodies as well as on joint F in order to generate enough information to solve for the unknowns. For the solution presented here, free body diagrams 1, 2, and 4 are selected. If we like, we can go back after the solution and use free body diagram 3 to confirm our results by checking that 3's equilibrium equations are identically satisfied. This is again a consequence of imposing equilibrium on overlapping components of an assembly. You may notice that I chose to place all of FCF on member CDE rather than placing it on ABC or splitting it up in some way between the two members. This choice is entirely arbitrary. Had I elected to place FCF on member ABC, the free body diagrams of ABC and CDE would differ, and as an alternative, I'm going to call these 2' and 3'. These are not in addition to 2 and 3. These would be in place of 2 and 3. By choosing to move FCF to a different location, I may have different internal forces that develop at C, and I want to make a distinction between those that are labeled in the free body diagram set 2 and 3 and those in the set 2' and 3'. So I'm going to call these CX' and CY'. And now I'm going to put all of FCF on ABC. Then on 3', I would have equal and opposite forces here. This would be CX', this would be CY'. FBF and FDF are going to maintain that 3, 4, 5 triangle, so I'm not going to sketch it in again. Here I've labeled the internal forces between members differently, primed versus unprimed, and we will generally get different numbers for the primed and unprimed values, but the net force on each member at C will be the same. In the present case, comparing free body diagrams 2 and 2' or free body diagrams 3 and 3' indicate that a single valued force on either member at C requires that CX should turn out to be the same as CX', but that CY and CY' will be related this way, CY plus FCF. This is perhaps easiest to see by comparing free body diagrams 3 and 3'. CY plus FCF from free body diagram 3 has to match CY' from free body diagram 3'. We'll set that aside for now, but we'll come back to it after we've looked at our solution. Okay, so to start with, what we're going to do here is use free body diagram 1, which will give us A, EX, and EY, and we'll take that information and go to free body diagram 2. Having A from free body diagram 1, we'll be able to solve for CX, CY, and FBF, and then knowing FBF, we'll be able to take that and go to free body diagram 4 and solve for FCF and FDF. So we'll be able to go sequentially from 1 to 2 to 4 to solve for all the unknowns of interest to us in the problem. For free body diagram 1, Force equilibrium in the x direction gives us Ex equals 0. Force equilibrium in the y direction gives us A plus Ey is 500 pounds. Sum of the moments about A equal to 0 gives us Ey times 200 inches minus 500 pounds times 60 inches equals 0. Together, that gives us Ey equals 150 pounds and A is 350 pounds. Now looking at free body diagram 2, we know A, so we can take moments about C in order to get FBF. We have from the external load 500 pounds times 40 inches minus the vertical component of FBF times 40 inches, that's minus 3/5 FBF times 40 inches. And now we know that A is 350 pounds, and so that's going to be minus 350 times 100 inches equals 0. And if we solve for that, we get FBF is equal to minus 625 pounds. Now the fact that turned out to be negative tells me that FBF actually isn't in compression, it's in tension, but we'll just leave it for now and continue. If we now write sum of the forces in X equals 0, we have Cx minus the horizontal component of FBF, which is 4/5 FBF, equals 0. And that gives us Cx equals minus 500 pounds. And finally, in the vertical direction, we have Cy plus A, which is now known as 350 pounds, minus 500 pounds from the external load, and plus the vertical component of FBF. But 3/5 of FBF is minus 375 pounds, and what we end up with is Cy ends up being 500 plus 375 minus 350, or 525 pounds. Finally, we take this information into the joint free body diagram 4, And horizontal equilibrium is going to tell us that the forces carried by BF and DF are the same. So DF is carrying the same load as BF is minus 625 pounds. Finally, vertical equilibrium tells us that FCF minus the two vertical components on either side of it, minus 3/5 FBF minus 3/5 FDF are 0, and that tells us that FCF is minus 750 pounds. Note that most of these unknowns yielded negative numbers. This simply means I guessed their direction incorrectly when I drew the free body diagrams. This is not a problem, it just means the forces actually go in the other direction from how I represented them initially. Suppose I now use all of my known forces to fill in the free body diagram for CDE. This is free body diagram 3. So I'll just say that we're going to use 3 as a check. And now I'll sketch this with the correct directions for everything. So we have our 150-pound reaction force here. And I had represented FDF in compression. I now know that it actually goes the other way, so that was 625 like this. I had represented FCF in tension, but that actually goes the other way. It's in compression, so it's pushing up 750 pounds. I had the direction of CY correctly. That was 525 in the direction it was shown here. And CX actually went in the other direction. It was negative. So that's 500 pounds actually this way. Now, if I've done everything correctly, this should automatically be in equilibrium, and we can see that that's going to be the case. So in the X direction, I have a 500-pound force in CX that's offsetting the horizontal component of the 625-pound force from FDF, and so I end up with 500 minus 4/5 of 625 is 500 minus 500 is identically 0. If I look at vertical equilibrium, I have a net on the left side at C. I've got 750 up minus 525 down. That's a net 225 pounds up. And if I combine that net 225 up with the plus 150, that's a net 375 pounds up, which exactly offsets the downward component of the 625-pound force from FDF. So 225 plus 150 minus 3/6 of 625 is 375 minus 375, which is identically 0. And if I choose to take moments about C, I'm going to get just contributions from the 150-pound force and the 625-pound force, at least its vertical component, and I would find that that again is identically satisfied. So here again we can go back after the fact and use our leftover free body diagram as a check on what we've done. Now to close, let's do a couple of other things. Let's suppose that, let's go back up to here, now and just remind ourselves of our alternative set of free body diagrams here, 2' and 3'. Suppose I had used this instead of 2 and 3. So how would that have changed the problem? Okay, so now we'll call it solution 2. Which is going to consist of the free body diagram set 1, 2', 3', and 4. Again, now we won't need all of those together. They'll be overlapping just as 1, 2, 3, and 4 were. In this case, what I'm going to do is suppose that I went, let's suppose that I went from 1 to 3' to 4. So I'm going to focus on CDE after I've solved for the reactions for the whole assembly. So if I do that, if I just repeat my free body diagram that I had above for CDE now with all the force from CF going on joint C of member ABC, then my free body diagram here is going to look like this. Here's FDF. We would have already solved for our reaction at E. We've got 150 pounds here. And we would have CX prime and CY prime like this, as we did above. You should confirm that if we take sum of the moments about C here and set that equal to 0, that will again give us FDF is minus 625 pounds, just as it was before, and that sum of the forces in Y equals 0 then give us CY prime equals minus 225 pounds. For completeness, you can show that sum of the forces in X equals 0 will give us CX prime is minus 500 pounds, as it was before. And this is entirely consistent with what we had earlier. We had, by comparing free body diagrams 2 and 2' or 3 and 3', we had that CX would have to be equal to CX prime to have a single valued X component of force at C, and that CY plus FCF would have to be equal to CY prime. So here we had minus 500 pounds for both of these, and we have here 525 plus minus 750 equals minus 225. So these are all consistent. And this confirms that it makes no difference how we apportion FCF between ABC and CDE. Finally, we could have split up FCF in some other way. We could have, for instance, placed half of FCF on ABC and the other half on CDE, or we could have used whatever fractional apportionment we wanted. Note that although this is permissible, it requires a more circuitous solution, as both ABC and CDE now have 4 unknowns. We would have to obtain a partial solution for one of the members, taking moment equilibrium about C for instance, bring the known force, either FBF or FDF, to joint F to solve for the other two forces at F, then bring the now known force FCF back to the original body to complete its equilibrium. As with many other choices we encounter, it is best to make choices that simplify our analysis if possible.